Okay, let's get started with knowledge-based AI. Today we'll talk about semantic networks. This is the kind of knowledge representation scheme. This is the first lesson in our fundamental topics part of the course. We'll start talking about knowledge representations, then we'll focus on semantic networks. We'll illustrate how semantic networks can be used to address 2x1 matrix problems. You can think of this like a represent and reason modality. Represent the knowledge, represent the problem, then use that knowledge to address the problem. As simple as that. At the end, we'll close this lesson by connecting this topic with human cognition and with modern research in AI. So what is a knowledge representation? The collage on the screen shows several knowledge representations that AI has developed. In each knowledge representation, there is a language. That language has a vocabulary. Then, in addition to that language, in that knowledge representation is some content. The content is some knowledge. Let's take an example with which you probably already familiar. Consider the Newton's second law of motion. So I can represent it as F is equal to ma. This is a knowledge representation, a very simple knowledge representation in which there are two things. There is a language of algebraic equations, y is equal to bx, for example. And then there is the content of our knowledge of Newton's second law of motion. Force equals mass times acceleration. So the knowledge representation has two things. Once again, the language, which has its vocabulary, for example, the sign of equality, and the content that goes into that representation expressed in that language. Let us not worry too much about all the representations on this collage right now. We'll get to them later. The idea here is to simply show that AI has developed not one, but many knowledge representations. Each representation has its own affordances and its own constraints. To understand semantic networks as a knowledge representation, let us take an example. This is an example that we saw in a previous lesson. This is A is to B as C is to D, and we have to pick one of the 6 choices at the bottom that will go in D. How will we represent our knowledge of A, B, C, and the 6 choices at the bottom? Let us begin with A and B. We will try to build semantic networks that can represent our knowledge of A and B. Inside A is a circle. I'll label it X. Also inside X is a diamond. I'll label it Y. Here is a black dot. I'll label it Z. We can similarly label the objects in B. So inside A are 3 objects, X, Y, and Z. So the first thing we need to do in order to build a semantic network for representing our knowledge of A is to represent the objects. So I have the object X, the object Y, the object Z, standing for the circle, the diamond, and the black dot. Now that we have represented the objects in A, we want to represent the relationships between these objects. So I have the objects X, Y, Z, and we'll try to represent the relationship between them by having links between the nodes representing the objects. These links can be labeled. So I may say that Y is inside X because that is the relationship in the image A. Similarly, I may say that Z is above Y because Z is above Y in the image A. I may also say that Z is above X because Z is above X in image A. In this way, a semantic network representation of the image A captures both the objects and the relationships between the objects. We can do exactly the same thing for the image B, the objects and the relationships between them. Y is above X. Now that we have represented our knowledge of image A and our knowledge of image B, we want to capture somehow the knowledge of the transformation from A to B, because recall A is to B as C is to D. So we want to capture the relationship between A and B, the transformation from A to B. To do that, to capture the transformation from A to B, we'll start building links between the objects in A and the objects in B. Now, for X and Y, that is straightforward. For Z, well, there is no Z in B. So we'll have a dummy node here in B, and we will see how we can label the link here so that we can capture the idea that Z doesn't occur in B. So we might say that X is unchanged because x, the circle here, is the same as the circle here. Y, on the other hand, has expanded. It was a small diamond here, and it's a much bigger diamond there. Z, the black dot, has disappeared altogether, so will say it's deleted. It's not there in B at all. I hope you can see from this example how we constructed a semantic network for the relationship between the images A and B. There were three parts to it. The first part dealt with the objects in A and the objects in B. The second part dealt with the relationships between the objects in A and the relationship between the objects in B. The third part dealt with the relationship between the objects in A and the relationship between the objects in B. In principle, we can construct semantic networks for much more complicated images, not just A and B. Here is another example of a semantic network for another set of images. Once again, we have the objects and the relationships, and then the relationship between the objects in the first image and that in the second image. Okay, this is becoming interesting. Now that we have done an example, let's do an exercise together. So this is the example A is to B on the left that we just did together. David, are you with me?
I'm with you.
Okay, very good. Here is C, and I've just chosen one of the choices out of the 6 choices, 5 here. And so we're going to try to build a semantic network for C and 5, just the way we built it for A and B. So for C and 5, I have already shown all the objects. Now your task is to come up with the labels for the links that are between these objects here, as well as the label for the link between the object for 5. Okay, let's do this exercise together. David, what did you come up with the labels for the various links?
So I looked at the vocabulary we used over here and decided to use the same vocabulary over here. Just like Z was above both X and Y, T is above both S and R. So I said T is above S and T is above R. Just like Y was inside X, S is inside R. So I said that S is inside R. Over here, I saw that S is above R, just like Y was above X. So I said S is above R.
Now David made an important point here. He said that the vocabulary he's using here of inside and above is the same as the vocabulary that I had used of inside and above here. And that's a good point because we want to have a consistent vocabulary throughout the representation for the class of problems. So here we have decided that for representing problems of this kind in semantic networks, we will use the vocabulary of inside and above, and we'll try to use it consistently. Let's go one step further. Now we have the semantic network for C and the semantic network for 5, but we have yet to capture the knowledge of the transformation from C to 5. So we have to label these 3 links. Let's do this exercise together. David, what labels did you come up with?
So just like I tried to transfer the vocabulary we used to describe the relationships between shapes in a figure, I decided to try and transfer the vocabulary we used to describe transformations between the 2 figures. So just like X was unchanged between A and B, R is unchanged between C and 5. In this case, S is also unchanged. It moved, but that's captured in the relationship between the shapes in figure 5. The shape itself hasn't changed, so it's unchanged. Just like .z disappeared, .t also disappeared, so I marked it deleted like we did before.
Good. That seems like a good answer. Now that we have seen some examples of semantic networks, let us try to characterize semantic networks as a knowledge representation. A knowledge representation will have a lexicon that tells us something about the vocabulary of that representation language, a structure which tells us about how the words of that vocabulary can be composed together into complex representations, and the semantics, which tells us how the representation allows us to draw inferences so that we can in fact reason. In case of a semantic network, the basic lexicon consists of nodes that capture objects, so X, Y, Z. What about the structural specification? Structural specification here consists of links, which have directions. These links capture relationships and allow us to compose these nodes together into complex representations. What about the semantics? In case of semantics, we're going to put labels on these links, which are then going to allow us to draw inferences and do reasoning over these representations. Now that we have seen semantic networks in action, we can ask ourselves an important question. What makes a knowledge representation a good representation? Well, a good knowledge representation makes relationships explicit. So in the 2x1 matrix problem, there were all of these objects, circles and triangles and dots. And there were these relationships between them, left off and inside. And the semantic network made all of them explicit. It exposed the natural constraints of the problem. A good representation works at the right level of abstraction, so that it captures everything that needs to be captured and yet removes all the details that are not needed. So representation, a good representation is transparent, concise, captures only what is needed, but complete, captures everything that is needed. It is fast because it doesn't have all the details that are not needed, and it is computable. It allows you to draw the inferences that need to be drawn in order to address the problem at hand. So what's a good representation from everyday life? David, can you think of an example?
So a good example that comes to mind pretty quickly for me is the example of the nutritional information on the side of a food or beverage container. It lists slots for each different kind of nutrient and also lists the quantity that's present in that food. So it seems like it's a pretty good representation of what's actually going on inside the food container.
What do you think? Do you think David is right? Let us think through this a little bit more deeply. Does the nutritional label make all the information explicit, David?
So it seems like it does. For each given nutrient in the food, it lists the explicit amount of that is present in the food. So it seems like it makes all the information explicit.
Would you say then it enables me to draw the right kind of inferences?
Well, it certainly seems like it does. So if I'm worried about my diet and I'm worried about how many calories I'm consuming, it tells me right there on the label exactly how many calories it has. So I can infer the right amount of food to eat per day. If you're concerned with something different in your diet, though, it actually gives you the information to make a different kind of inference.
What about extraneous information, information that I may not need?
Well, that's a good point, actually, because it gives the information that anyone might need, and as a result, it's going to give information that's extraneous to somebody. So, for example, in my diet, I might not care about the number of carbohydrates I consume. So for me, that's extraneous information, but for somebody else, that's very important. So it doesn't avoid extraneous information, but it would be really hard for it to do so.
What about relationships? Does it make all the concepts and all the relationships between them really explicit?
So actually, now that you mention it, Ashok, it really doesn't. So for example, the number of calories from fat in a particular food is based in large part on the amount of fat that's in it. It gives the number of calories from fat and the amount of fat in it right there on the label, but it doesn't tell me that there's a relationship there. So I really can't make any inferences based on that relationship. I don't even know that relationship exists.
So note how this connects with the ability to make inferences. Nutritional labels capture some information that allows us to make good inferences, do not capture all the information. Let us now look at a different problem, not the 2x1 matrix problem, but a problem called the guards and prisoners problem. Actually, this problem goes by many names: the cannibal and missionaries problem, the jealous husbands problem, and so on. It was first seen in a math textbook about 800 AD. And it will be used by many people in AI for discussing problem representation. Imagine that there are 3 guards and 3 prisoners on one bank of a river, and they must all cross to the other bank. There is one boat, just one boat, and that can only take 1 or 2 people at a time, not more, and the boat cannot travel alone. On either bank, prisoners may never outnumber the guards, because if they do, they will overpower the guards. So the number of guards must at least be equal to the number of prisoners on either bank. We'll assume these are good prisoners. They won't run away if they're left alone, although they might beat up the guards if they outnumber them. That's the beauty of this class. We deal with real problems, practical problems. We'll also make up problems to help illustrate specific things. I think you're going to have fun with this one. Let us try to construct a semantic network representation for this guards and prisoners problem and see how we can use it to do the problem solving. So in this representation, I'm going to say that each node is a state in the problem solving. In this particular state, there happens to be one guard and one prisoner on the left side. The boat is on the right side, and 2 prisoners and 2 of the guards are also on the right side. So this is a node, one single node. So the node captured the lexicon of the semantic network. Now we'll add the structural part, and the structural part has to do with the transformation. That is going to connect different nodes into a more complex sentence. We'll label the links between the nodes, and these labels then will capture some of the semantics of this representation that will allow us to make interesting inferences when it comes time to do the problem solving. Here is the second node, and this node represents a different state in the problem solving. In this case, there are 2 guards and 2 prisoners on the left side. The boat is also on the left side, and there is 1 guard and 1 prisoner on the right side. So this now is a semantic network. A node, another node, a link between them, and the link is labeled. Note that in this representation, I used icons to represent objects, as well as icons to represent the labels on the links between the nodes. This is perfectly valid. You don't have to use words. You can use icons as long as you're capturing the nodes and the objects inside each state, as well as the labels on the links between the different nodes. There is an old saw in AI, which goes like, if you have the right knowledge representation, problem solving becomes very easy. Let's see whether that old saw works here. We now have a knowledge representation for this problem of guards and prisoners. Does this knowledge representation immediately afford effective problem solving? So here we are in the first node, the first state. There are 3 guards and 3 prisoners on the boat, all on the left-hand side. Let us see what moves are possible from this initial state. Now, using this representation, we can quickly figure out that there are 5 possible moves from the initial state. In the first move, we move only 1 guard to the right. On the second move, we move a guard and a prisoner to the right. In the third move, we can move 2 guards or 2 prisoners. Or in the fifth move, just 1 prisoner to the right. 5 possible moves. Of course, we know that some of these moves are illegal and some of them are likely to be not very productive. Will this semantic network allow us to make inferences about which moves are productive and which moves are not productive? Let's see further. So let's look at the legal moves first. So we can immediately make out from this representation that the first move is not legal because we are not allowed to have more prisoners than guards on one side of the river. Similarly, we know that the third move is illegal for the same reason. So we can immediately rule out the first and the third moves. The fifth move too can be ruled out. Let's see how. We have 1 prisoner on the other side, but the only way to go back would be to take the prisoner back to the previous side. And if we do that, we reach the initial state, so we did not make any forward progress. Therefore, we can rule out this move as well. This leaves us with 2 possible moves that are both legal and productive. We have already removed the moves that were not legal and not productive. Later, we will see how AI programs can use various methods to figure out what moves are productive and what moves are unproductive. For the time being, let's go along with our problem solving. Okay, now that we have come thus far, let's go one step further. For each of these 2 states, there is only 1 possible legal and productive move that can follow. What is the legal and productive move from this state? And what is the legal and productive move from this state? Can you please fill out these boxes?
Write the number of guards on the left coast in the top left box, just as a number 0, 1, 2, or 3. The number of prisoners on the left coast in the bottom left box. The number of guards on the right coast in the top right box. And the number of prisoners on the right coast in the bottom right box.
So what answers did you come up with, David?
So we knew that because the boat is traveling from the right back to the left, that the boat is going to be on the left in each of the next states. So we didn't even ask for that. In the top state, the only things we could do are move both people back, just the guard back, or just the prisoner back. Moving both back would just take us back to our original state, so while it's legal, it's not productive. Moving just our prisoner back would have more prisoners on the left than guards, so that wouldn't be a legal move. So our only move is to move our guard back to the left. Similarly, on the bottom, we could either move both prisoners back to the left, or just 1. Moving both would take us back to our original state, which isn't productive. Moving just 1, then, is our only legal next state.
That was a good answer, David. Thank you. Note, David, that these 2 states that you came up with, the one at the top here and one at the bottom here, are in fact identical. And because they are identical, therefore we can collapse them into 1 state. So now we get the representation shown in this figure. The 2 states have been collapsed into 1.
So in this semantic network, we don't really care how we got into a state, just as long as we know what state we're in. And that makes sense in this problem-solving process. Once we're in this state, we don't care if we got to it this way or this way. All we care about is the current state of the problem.
Let us take this problem solving a little bit further. Now that we are at this state, let us write down all the legal moves that can follow. It will turn out that some of these legal moves will be unproductive. But first, let's just write down the legal moves that can follow from here. David, did you solve this problem?
So just like the original state, there could be 5 moves that come out of this. 2 of the moves we can already say are illegal. Moving 2 guards would have more prisoners than guards on the left, and moving 1 guard and 1 prisoner would end up with too many prisoners on the right. So we don't include those states. Then our 3 legal moves are to move 1 prisoner, 2 prisoners, or 1 guard. But now I notice that this state is actually identical to this state. Like we said before, once we're in a state, we don't really care how we got there, so going back to an earlier state is not a productive move. So we can rule this out as an unproductive move. Similarly, this state is the same as this state. So we can rule this out as an unproductive move as well. That leaves us with only 1 legal productive move that can follow from the previous state.
That is a very good point, David. So this representation is a good representation for this problem because it is making all the constraints of the problem solving explicit so that we can quickly compare states and say which moves are productive and which moves are not productive.
I can tell you that when I tried to solve this problem on my own, it took me a while because I didn't recognize the fact that I kept going around in a circle because I didn't realize I kept coming back to the exact same state.
In fact, David, most of us have the same difficulty. So the power of this semantic network as a representation is arising because it allows us to systematically solve this problem, because it makes all the constraints, all the objects, all the relationships, all the moves very explicit. We can continue this problem-solving process further and solve this guards and prisoners problem. I'll not do that here, both because it will take a long time and because the entire picture will not fit into the screen. But I would like you to do it yourself, and I want you to do it and tell me how many moves does it take to move all the guards and all the prisoners from one side to the other side of the river. Once you're done, once you have solved the problem and moved all the guards and prisoners to the other side, write the number of moves here in this box. How many moves did you come up with, David?
So I was able to do the problem in 11 moves. I won't talk you through the entire process, but if you'd like to pause this video, you can take a look and see the exact moves I used and see if they match yours. We know that 11 moves are the most efficient way to solve the problem, but these aren't the only 11 moves that can actually solve the problem.
Good, David. That's the correct answer. So now that we have solved this problem together, next time you go to a cocktail party, you can entertain all of your guests by showing how you can do this problem so effectively and so efficiently, even as all of them flounder trying to do things on their napkin and not succeeding.
So we've not yet talked about how an AI method can determine which states are productive and which states are unproductive. We'll revisit this issue in the next couple lessons.
Now that we have seen how the semantic network knowledge representation enables problem solving, let us return to that earlier problem that we were talking about, the problem of A is to B as C is to 5. Recall that we had worked out the representations for both A is to B and C is to 5. The question now becomes whether we can use this representation to decide whether or not 5 is the correct answer. If we look at the 2 representations in detail, then we see much of the representation here is the same as the representation here, except that this part is different from this part. Here we have Y expanded, and where here we have S remain unchanged. So this may not be the best answer. Perhaps there is a better answer, where the representation on the left will exactly match the representation on the right. So let us do another exercise together. This time I've picked a different choice 2 here. So now we can build a representation for A is to B, like earlier, and here is a representation of C is to 2. I would like you to fill out these boxes for the labels on the links here, and then answer whether or not 2 is the right answer for this problem. What answer did you come up with, David? Is 2 the correct answer?
So I said that that was the correct answer. It looks to me like the relationships at play in frame A and frame C are the same, and the relationships at play in frame B and frame 2 are the same. We saw that X was unchanged between the 2 frames, just as R is, Y expanded, just as S does, and Z was deleted, just as T is. Similarly, Y was above X, just as S is above R. So I think it's the right answer.
Good, David. That's in fact the correct answer. 2 is the best choice available here. But imagine that for 2 as well, the match between the representation on the left side and the representation on the right side was only partial, just like it was when we had 5 here. How then would we make a choice between 2 and 5, David?
So it sounds like so far we've been talking about kind of an all or nothing match of transformations. But if we didn't have an exact match between the transformations, we'd have to come up with some way to evaluate how well two transformations actually fit together. So we might say that these transformations are 95% similar, while these two are only 70% similar. So that would allow us to choose one over the other.
That sounds fair. In fact, we'll come across something like this very soon. Let us do another exercise. This is actually an exercise we had come across earlier. However, this exercise has an interesting property. Often the world presents input to us for which there is no one single right answer. Instead, there are multiple answers that could be right. The world is ambiguous. So here we again have A's to B, C's to D, and we have 6 choices. So what choice do you think is the right choice here? What answer did you think about, David?
So this is a tiny bit different than the one we saw earlier. Earlier we saw this exercise without the square as an option, so we were forced to pick the triangle. But here, since we actually have the square as the option, I think the easier transformation is to say that the middle shape is disappearing, and thus the triangle disappears and leaves us with just that square. So I'd say that 5 is the correct answer.
That's a good answer, David. But note that 3 could also be an answer, because one could imagine the relationship between A and B a little differently. Suppose we were to say that the outer circle is disappearing and the inner circle is expanding. In that case, we'll again get B. So in that case, we might say that the outer image is disappearing, the square, and the inner shape is expanding to give us 3. So 3 is also a legitimate answer.
So I imagine, though, that most people would choose answer 5 over answer 3. But why would most of us choose answer 5 over answer 3?
That's a great question. Let's look at this in more detail. So let us look at the semantic network representation of the relationship between A and B. In one view of the transformation from A to B, we can think of Q, the outer circle, as remaining unchanged, and P, the inner circle, as getting deleted. Let's look at another view of the transformation from A to B. In this view, we can think of P as getting expanded, and Q, the outer circle, as getting deleted. Both of these views are valid views. If both of these views are valid, then how would anyone decide? How would an AI agent decide which view to select? Let us suppose that the AI agent had a metric by which it could decide upon the ease of transformation from A to B. Let us suppose that that metric assigned different weights to different kinds of transformations. You will notice that these transformations like scaling, rotation, reflection make for affine transformations. In this scale, a larger value, like 5 points, means more ease of transformation and greater similarity. A lower value means less ease of transformation, a more difficult transformation, and less similarity. Given the scale, let us calculate the weight of transformations for both transformation number 1 and transformation number 2. In transformation number 1, you can see that P is getting deleted, which we gave a weight of 1, and Q remains unchanged, which we gave a weight of 5. So the total weight here is 6. In case of transformation number 2, the weight of P being expanded, we said will be 2, scaled, and Q getting deleted is 1, so the total weight is 3. If we prefer the first transformation over the second transformation, then we can see why someone will answer the square as the correct answer and not the triangle. Let us return to this exercise, and now we can see why both 3 and 5 are legitimate answers. We can also see why an AI agent may prefer 5 given the similarity metric that we talked about in the last chart. In order to make sure that we're getting the point here, let us revisit an exercise we had come across earlier. This is a truncated version of the exercise. That one had 6 choices. Here there are only 4 choices. The similarity weights are shown here. David, which one do you think is the right choice for this problem?
So it seems to me that given these 4 choices, the right choice is going to be number 2.
What does everyone think about David's answer? Did David give the right answer with 2? What does everyone think? Is 2 the right answer here? Well, let's look at the choices. First, note that both 2 and 4 are legitimate answers. 2 is legitimate because we can think of the transformation from A to B as a reflection along the vertical axis. And so if we think of the transformation from C to D, again as a reflection along the vertical axis, we'll get 2. 4 is also a correct answer because we can think of the transformation from A to B as a rotation of 180 degrees. And if we rotate C by 180 degrees, we'll get 4. However, if we look at our weights again, we gave reflection a higher weight than we gave rotation. And therefore, David is right. 2 indeed is the correct answer. Before we end this lesson, I want to draw several connections. The first has to do with memory. We have often said that memory is an integral part of the cognitive systems architecture. One can imagine that A and B are stored in a memory. Then C and 1, and C and 2, and C and 3, and so on are probes into the memory. And the question would then become, which one of these probes is most similar to what's stored in memory? We might decide on that answer based on some similarity metric. In fact, we'll revisit this exactly the same issue when we talk about case-based reasoning later on in this class. Another connection we can draw here has to do with reasoning. When we are talking about the transformation from A to B and then the transformation from C to one of these choices, one question that arose was, should we make the connection between the outer circle here and B or the inner circle in A and B? This is the correspondence problem. The correspondence problem is, given two situations, what object in one situation corresponds to what object in another situation? We will come across this problem again when we discuss analogical reasoning a little bit later. The third connection has to do with cognition or knowledge-based AI as a whole. Notice that instead of just talking about properties of objects, like this is a circle and the size of the circle, our emphasis here has been on the relationships between the objects. The fact that this is inside the outer circle, or the fact that the outer circle remains the same here, the inner circle disappears. In knowledge-based AI and in cognition in general, the focus is always on relationships, not just on objects and the features of those objects.
The first assignment you can choose to do for this course is to talk about how these semantic networks can be used to represent Raven's progressive matrices. We saw a few different problems in the first lesson, so take a look at how the semantic networks we've talked about today can be used to represent some of those other problems and write your own kind of representation scheme. In addition to writing a representation scheme, also talk about how that representation scheme actually enables problem solving. Remember what Ashok mentioned about the different qualities of a good knowledge representation, that it's complete, it captures information at the right level of abstraction, and it enables problem solving. So write about how your representation can enable problem solving of 2x1, 2x2, and 3x3 problems. You don't need to use the exact same representation scheme that we use, and in fact you can and should use your own. Also remember that your representation should not capture any details about what the actual answer to the problem is, but rather it should only capture what's actually in the figures in the particular problem. So let's recap what we've talked about today. We started off today by talking about one of the most important concepts in all of knowledge-based AI, which are knowledge representations. As we go forward in this class, we'll see that knowledge representations are really at the heart of almost everything we'll do. We then talked about semantic networks, which are a particular kind of knowledge representation, and we use those to talk about the different criteria for a good knowledge representation. What do good knowledge representations enable us to do, and what do they help us avoid? We then talked about kind of an abstract class of problem-solving methods called represent and reason. Represent and reason really lies under all of knowledge-based AI, and it's a way of representing knowledge and then reasoning over it. We then talked a little bit about augmenting that with weights, which allows us to come to more nuanced and specific conclusions. In the next couple weeks, we're going to use these semantic networks to talk about a few different problem-solving methods. Next time we'll talk about generate and test, and then we'll move on to a couple slightly different ones called means-ends analysis and problem reduction.
How are semantic networks connected with human cognition? Well, we can make at least two connections immediately. First, semantic networks are a kind of knowledge representation. We saw how if knowledge is represented as a semantic network, and if there is also a problem representation, then you can use the knowledge representation to address the problem. We can now say, similarly for human mind, that human mind represents problems, it represents knowledge, then it uses that knowledge to address the problem. So representation then becomes the key. Second, and more specifically, semantic networks are related to spreading activation networks, which is a very popular theory of human memory. Let me give you an example. Supposing I told you a story consisting of just 2 sentences. John wanted to become rich. He got a gun. Now notice that I did not tell you the entire story, but I'm sure you all made up a story based on what I told you. John wanted to become rich. He decided to rob a bank. He got a gun in order to rob the bank. But how did you understand the story? How did you draw the inferences about robbing a bank, which I did not tell you anything about? Imagine that you had a semantic network that consisted of a large number of nodes. So when I gave you the first sentence, John wanted to become rich, the nodes corresponding to John and wanted and become and rich got activated, and the activation started spreading from those nodes. And when I said he got a gun, then the gun node also got activated, and that activation also started spreading. As this activation spread, they merged and a pathway got formed. And all the nodes on that pathway now become part of the story. And if you happen to have nodes like rob a bank along the pathway, now you have an understanding of the story. Please write down what you learned in this lesson.
Great. Thank you so much for your feedback.